This problem is to find the interval of solutions for the inequality 3x plus 2 is less than 5x minus 8. In this type of problem, the goal is to get x all by itself, so it's clear what x is greater than or less than for the inequality to be true. We have a 3x and a 5x. We can subtract 3x from both sides. 3x minus 3x cancels out. We still have the 2 is less than 5x minus 3x is 2x. And we still have the minus 8. Now we want this x all by itself, so we need to add 8 to both sides to cancel out this 8. Two plus 8 is 10, is less than, all that's left is 2x. And we want this x by itself, so we divide both sides by 2. Ten divided by 2 is 5, is less than. 2x over 2 is just x. So we have 5 is less than x, for x is greater than 5. The problem stated to find the interval of solutions. We know that the solution is x is greater than 5, so that interval is 5 to positive infinity, not including 5, because this is greater than, not greater than or equal to. Another graphical way of looking at it is on the real number line. You have 5, and the curved line means not including 5. In this problem, we are asked to find the interval of solutions for the inequality, the absolute value of 2x plus 3 over 5 is less than 2. So we have an absolute value of a quotient here. And ask yourself, do you know any properties of inequalities that have to do with quotients? Well, one of them is if you have an absolute value of some a over b, this is equivalent to the absolute value of a over the absolute value of b. So we're going to use this to change this to the absolute value of 2x plus 3 over the absolute value of 5 is less than 2. So now we have this, and now the absolute value of 5 is just 5. So we can safely say that that equation is equal to this. The absolute value of 2x plus 3 over 5 is less than 2. And now, since 5 is a positive number, we can multiply both sides by 5 without changing the direction of the inequality. If we multiply 5, the 5's cancel out. 2 times 5 is 10. So now you have the absolute value of 2x plus 3 is less than 10. So now we have an absolute value expression is less than some non-negative number, 10. So do you remember any theorems about what you can do when an absolute value expression is less than some non-negative value? Let's say you have A is less than B for some B greater than 0. Think, do you know what to do, what you can turn this into? Well, what you can do is when you have the absolute value of A is less than B for some positive value B, this can be rewritten as you see, you can take off the absolute values and you can put it between the negative and positive of the non-negative value. So using this, we're going to take this 10 and we're going to say negative 10 is less than 2x plus 3, which is less than 10. So now we have this. And now to get the x by itself, we can multiply or add and subtract through. We can take this 3 by getting rid of it by subtracting all these things by 3. Negative 10 minus 3 is negative 13 is less than, all that's left here is 2x is less than 10 minus 3 is 7. Now, to get x, we can divide through by 2. So we have negative 13 divided by 2. We can say 13 halves is less than x is less than 7 halves. So we have x is greater than 13 halves and less negative 13 halves. Almost made a mistake. So x is greater than negative 13 halves and less than 7 halves. So going back to the original problem, the interval of solutions is the open-ended boundary between negative 13 halves and 7 halves. This is the answer. This problem states, find the interval of solutions for the inequality, the absolute value of 2x plus 1 is less than 0. So look at this problem. Sometimes you rush into a solution because you remember some theorem. You might say to yourself, I remember hearing that if the absolute value of A is less than some B, then I can transform this into minus B is less than A without the absolute values is less than B. But there's an important condition that applies to this theorem. Do you remember what it is? What is it about B that must be true for this to be a valid transformation? Of course, it's that B must be positive. So, is this valid here? So just for a moment, for fun, let's see where this leads us if we jumped in and started to use that theorem. So now we have negative 0, if that's such a thing, is less than 2x plus 1 is less than 0. We want to get what x is. So let's subtract through by subtracting 1 through everything. negative 0 minus 1 would be negative 1 is less than 2x is less than 0 is minus 1 is minus 1. Now, to get x by itself, let's divide everything by 2. So we're getting negative 1/2. X is greater than negative 1/2. And negative 1 divided by 2 again is negative 1/2. So x is greater than negative 1/2 and less than negative 1/2. Does that make sense? Can x be both greater than negative 1/2 and less than negative 1/2 at the same time? Of course not. So, if we stopped for a minute at the beginning and said, what do we know about absolute values? Can they ever be negative? Remember that they can't be negative. The condition for saying that the absolute value is less than some b is that this b is a positive number. So what does this mean? If the absolute value is never negative, then this is impossible. There is no interval. So the answer for this problem is there is no interval of solutions for which the absolute value of 2x plus 1 is less than 0. And that's the answer. This problem says find the interval of solutions for the inequality x squared minus 10x is less than or equal to 200. You could solve this problem a number of different ways. What I'm going to do is move over the 200 so that the problem becomes this. I'm going to subtract 200 from both sides. (200 minus 200 is 0. So now it's x squared minus 10x minus 200 is less than or equal to 0, or in other words, is negative. Now, if you've factored binomials before, you know that some are factorable in the way that I'm doing right now. Now, what factors of negative 200 add up to negative 10? Think about that. Now, you can do 20 and 10, because 20 times 10 is 200. Which one of these do we make negative? And which one do we make positive to add up to negative 10? Negative 20 plus 10 is negative 10, and negative 20 times positive 10 is negative 200. And for this product to be negative, one of these has to be positive and the other negative. So let's think about this for a minute. One of these will probably be impossible and one of them will work out. Let's say we want this to be positive and this to be negative. What value does x have to be for x minus 20 to be positive? Well, x has to be greater than 20. And for this x plus 10 to be negative, x has to be less than negative 10. Let's look at these. Can x be greater than 20 and less than negative 10 at the same time? No. So that's impossible. Then let's try making this one negative and this one positive. Now for this to work, x minus 20 to be negative, we just say x is less than 20. X plus 10 is positive. X has to be greater than negative 10. Now, can a number be greater than negative 10 and less than 20? Yes. And we're including zeros, so the interval is from negative 10 to 20. If x is in this range, then this product, which is equivalent to this, is negative or 0. So this interval is the solution. This is a pretty straightforward problem. It says find the interval of solutions for the inequality 0 is less than or equal to 4x minus 1, which is less than or equal to 2. And if you know how to perform the operations to get x all by itself, you can probably pause this problem and solve it very quickly, which is what we'll do right now. First of all, we've got this minus 1 right here, so to get this by itself, we add 1 to everything across the inequality. So we do plus 1, plus 1, plus 1, which gives us 0 plus 1 is 1, is less than or equal to 4x, is less than or equal to 2 plus 1 is 3. And to get the x all by itself, we divide through by what? 4. And 4 is a positive number, so the inequality does not change directions. One divided by 4 is 1/4, is less than or equal to 4x over 4 is just x, is less than or equal to 3 divided by 4 is 3/4. And so x is greater than or equal to 1/4 and less than or equal to 3/4. And this is a proof problem that says prove that the absolute value of a minus b is greater than or equal to the absolute value of a minus the absolute value of b. And with proof problems, you have to start with something that is accepted, whether it's an axiom or a theorem, and get through valid steps to the final equation or inequality that you set out to prove. So we have to start with something that we accept, and we have to end up with this. But what I'm going to show you first is a couple of useful theorems and definitions that will help us. First, let's remember the definition, or a good definition, of absolute value. We'll say that given that x is a real number, the absolute value of x is x if x is greater than or equal to 0, and negative x if x is less than 0. So take a look at this for a little while before we move on. The first consequence that we can reason out is that for all x, the absolute value of x is non-negative, because by the definition we just saw a few seconds ago, if x is non-negative, then the absolute value is x. And if x is negative, then the absolute value is the negative of it. The negative of a negative is non-negative. So therefore, for all x, the absolute value is always greater than or equal to 0. And another consequence due to the definition of the absolute value is that for all x, x is always less than or equal to the absolute value of x. Once again, if x itself is 0 or greater than 0, then the absolute value of x is the same as x. In this case, the equal would apply. But if x is negative, then the absolute value is the negative of the negative. And as we said in the first consequence, the absolute value is always greater than or equal to 0. So if x is less than 0, then x is less than the absolute value of x. So it's always less than or equal to the absolute value of x. These will be useful in this proof. And now we're going to build up another useful theorem, which you might have seen, I might have actually already used in this video, but now we're going to show that it always works. What I've got here is a table. I've got a column for the number of a statement line, and the statement and the justification. So we have to start out with something that we already accept, whether it's an axiom or a theorem. And as we go along, we can begin to use theorems for justification. You'll see how we work it. So we'll start out, we showed that for all x, x is always less than or equal to the absolute value of x. So let's put a statement here like 1. And we're going to use another letter for the real number in question. We're going to say some a, and it has to be an arbitrary. We're not saying any specific a. We're saying generally, and it has to be something that works for any value of a. In this theorem, it works. A is less than or equal to the absolute value of a. And what's the justification? It's that theorem 1. We can accept this because we accept this theorem as valid. Okay, here's another step 2. Now we're going to pick another random real number which does not have anything to do with a. We're going to say b is less than or equal to the absolute value of b. And the justification is that theorem 1, which says for any real number x, x is less than or equal to the absolute value of x. So these statements, a is less than or equal to the absolute value of a, is justified, and b is less than or equal to the absolute value of b, which is, oops, I shouldn't have written that, is justified. Now, here's a step 3. If a is less than or equal to the absolute value of a, and b is less than or equal to the absolute value of b, we can say that a plus b is less than or equal to the absolute value of a plus the absolute value of b. What is the justification? We can say that if step 1 is justified, step 2 is justified, and we can call it a common notion. There's probably a better. We're basically saying if something is less than another, and another thing is less than its other, then we can add the two lessers, and it will be less than or equal to the sum of the two greaters. We'll say that we can accept that. Okay. Now, step 4 is this. We should have defined this earlier. What I meant to say was we could have taken what I'm about to say and formalized it as another theorem, but just to be quick, what I've said here is if you accept this as a theorem, and if you accept that x is always less than or equal to the absolute value of x. Now, if you take the negative of the absolute value of x minus absolute value of x. Now, if x is negative, then this and this are equal. But if x is a positive value, and if the absolute value of x is always a positive value, then the negative of the positive value is negative. Then this will be less than x. And so what I did was I took 1 and 2 and I added them together, and I said that the negative of this sum is less than or equal to the sum of them. Take a minute if you're not convinced. If you take steps 3 and 4 together as justification, you can build this statement, which says the negative of the sum of the absolute value of A and the absolute value of B is less than or equal to A plus B, which is less than or equal to the sum of the absolute value of A and the absolute value of B. I should have brought this up earlier as another useful theorem, but I forgot to. What I've written up here is let's quickly get established some theorem which we'll call theorem 2. Let B be some positive number right here. We'll assume that B is a positive number. It's greater than or equal. Well, it's non-negative. B is greater than or equal to 0. What we want to say is if some value A is greater than or equal to minus B and less than or equal to B, if that is true, then we want to show that the absolute value of A is less than or equal to B. Now, what I've done here is through previous foundational work, we can say that A is always between the negative absolute value of A and the positive. Well, absolute value is always positive. So A is always between the negative of its absolute value and its absolute value. If A happens to be negative, then it's equal to this. If A is non-negative, then it's equal to this. But in all cases, it's between the negative of the absolute value and the absolute value. And remember, we assumed this. So what we can do is we can say if A happens to be negative, then it's equal to the negative absolute value of itself. And we said if negative B is less than or equal to A, then it's less than or equal to the negative of the absolute value of A. Now, if A happens to be non-negative, and we accept that it is less than or equal to this non-negative B, if it's non-negative, then absolute value of A is equal to A, which means that it is less than or equal to B. So, in all cases, the absolute value is less than or equal to B. This is what we want. So if we assume this logically follows. And what I've done down here is I'm going to add another justification right here, given this theorem 2 that we have supposed we have sufficiently proven. We're saying now that if you have step 5 here, negative of the sum of the absolute value of A and the absolute value of B is less than or equal to A plus B is less than or equal to the sum of absolute value of A and absolute value of B. In this case, this thing in the middle is like this A. And you can see this and this are the same thing, but this one has a negative in front of it. So in this case, absolute value of A plus absolute value of B is like the B in Theorem 2. So if this thing is always between the negative of this, and the sum of two absolute values is always non-negative, then by Theorem 2, and given that we accept line 5, we can say the absolute value of this will be less than or equal to this. The absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. And this theorem has a name. It is often called the triangle inequality. So we'll add that along with Theorem 2 to our list of theorems that we're going to use in this problem. Okay, now that we've established some of these theorems, we can start to do the proof. Now, let's start out with this. The A, given any random A, is less than or equal to the absolute value of A. The justification is Theorem 1, because we proved that this step is valid for all real number values of A. I put back on the board what exactly we're trying to prove. We're trying to get from valid starting statements to this. We're trying to prove that the absolute value of A minus B is greater than or equal to the absolute value of A minus the absolute value of B. And we have these things to work with, and we've started with this. And this is where we have to start getting creative. So one thing, without giving too much of a hint at first, I'll tell you lots of proofs. One of the tricks or techniques that you see is you take something and you add and subtract the same value so that it's not changed at all, but you can take part of it and do something with it. So with that hint, starting with this, and given that we want to get to this and that we have these to work with, take that hint. Let's see if we can add and subtract back something somewhere in here. So pause the video, think about that. Think about what you could do with this, and then we'll move forward. Okay, look what I wrote down on line 2. Here we have, back on line 1, A is less than or equal to the absolute value of A. Here it is again, A is less than or equal to the absolute value of A. Now look at this. What do you get if you have A minus B plus B? The minus B and the plus B cancel out, so this is actually equal to the absolute value of A. So what I wrote was A is less than or equal to the absolute value of A, which, since it's equal to the absolute value of A, and this is the absolute value of A, we can say that the absolute value of A is less than or equal to the absolute value of the quantity A minus B plus B. So now that I've done that, take a look at this, the triangle inequality, and look at what we're trying to get to. And what we've got so far and see what conclusions you can make. I encourage you to pause the video and think about this for a little while. Here's one quick hint. Now, when you have an inequality, you can always subtract through all parts of the inequality the same thing, and the inequality will remain true. So as you're looking at this and you want to get to this, here's a hint. Think about what you would like to subtract here, here, and here. All right, what I've written in 3 is actually another form of the triangle inequality. Now remember, this says that the absolute value of sum A plus sum B is less than or equal to the absolute value of A plus the absolute value of B. Now let's rewrite this using, instead of just an A right here, let's use the symbol A minus B. And for B, we'll still use B. We're saying this is this A minus B, and this is B. So everywhere you see an A, replace it by an A minus B. So here we have the absolute value of A minus B plus B is less than or equal to the absolute value of A minus B plus the absolute value of B. So as you can see, this is a form of the triangle inequality right here. Now guess what we'll do next. If we have this and we want to get to this, think about what to do next. All right, what I've done on step 4 is, given step 3, and given that A minus B plus B is simply A, I've just rewritten it more simplified. So this is the absolute value of A is less than or equal to the absolute value of A minus B plus the absolute value of B. Now we're very close. Compare this. Absolute value of A is less than or equal to absolute value of A minus B plus absolute value of B. Look what we want to prove right here. So what do we subtract from both sides of this inequality on line 4 to get the inequality that we set out to prove? If you noticed that we could subtract the absolute value of B from both sides, you were right. Here on line 5, we've taken the inequality on line 4 and we've subtracted the absolute value of B here. So we've got the absolute value of A minus the absolute value of B is less than or equal to, and then this side there was the absolute value of A minus B plus the absolute value of B. Now if we subtract the absolute value of B here, the absolute values of B go away and we have the absolute value of A minus B. And this is what we wanted to prove. So we've proven that the absolute value of A minus the absolute value of B is less than or equal to the absolute value of A minus B. So perhaps the least intuitive step was adding and subtracting the same value within a given expression. And the ability to see when that is useful will come with experience, which is why it's useful to solve lots of problems. And so now we've proven what we set out to prove. This problem says if 0 is less than A, which is less than B, prove that 1 over a is greater than 1 over b. And why is the restriction a is greater than 0 necessary? So for this one, we get the starting premise that a and b are both positive and b is greater than a. And starting with that premise, we need to arrive at a conclusion that the reciprocal of a is greater than the reciprocal of b. So think about what theorems you know and what you can use, and try to work on this. And in a moment, after pausing this, I'll show you my method. The truth is that I worked at this for a while, and the proof itself turned out to be not very long at all, but a couple of the steps involved in the proof that I came up with depended upon some steps that seemed pretty sound to me, but I wanted to work out that they were actually logically correct. And so before I start, I'll show you one definition that I wanted to state formally, and after that I'll show you one useful theorem or lemma that I came up with and proved that it was correct. And after that, I'll show you my proof that uses that definition and that lemma. Here's where I formally state what a reciprocal is. I said let x be a real number not equal to 0. Then when I write 1 over x, I mean the real number which, when multiplied by x, equals 1. So for all x not equal to 0, 1 over x times x equals 1. Here's the next thing that I wanted to use during my proof, so I went ahead and proved it in advance. I called it lemma L1. I said to myself, let x and y be positive real numbers. So x and y are both positive. X is less than y if and only if y over x is greater than 1. And so to prove this, I have to prove that if x is less than y, then y over x is greater than 1. And then I also want to prove if y over x is greater than 1, then x is less than y. And so I'll prove both of those next. And first I want to prove that if x and y are both greater than 0, I want to prove that if x is less than y, then y over x is greater than 1. So to prove that x less than y, both positive, implies y over x is greater than 1, I went with a geometric style of proof. I said, okay, we're taking it for a given that x and y are greater than 0 with x less than y. I said, let's take x, capital X, let capital X be a line segment, lowercase x, units in length. So what that means is, let's take this line segment, capital X, and this could be each of these segments, each of these subsegments that I'm drawing is 1 unit in length, and so on, all the way to here. And there are lowercase x of these. So if capital X is a line segment, little x units in length, then the total length is little x units. Okay. Okay, and then let me say that capital Y is a line segment, lowercase y, units in length. So here's line segment Y. with lowercase y number of unit length segments. And here they are. I've drawn them. We're starting with the proposition that y is greater than x. So that's why I drew y, line segment y, longer than line segment x, because there are more line segments, and each of these line segments is uniform, but in line segment y there are more of them, which is why line segment y is longer. And so now that we've established that we have this line segment with more units than this one, we'll move on to the next step. So just to restate yet again, in case I didn't state it, we're saying that y is longer than x. It has more units. So we're saying y has more units than x by some positive number of units, k. In other words, y equals x plus k for some k which is greater than 0. Then the ratio of units in y to the number of units in x is y over x. And since y equals x plus k, we can say that y over x is equal to x plus k over x. And this fraction can be rewritten as x over x plus k over x for some positive value k. X over x is equal to 1. So that means it's equal to 1 plus k over x. And since k is some positive value and x is a positive value, we can say that this is greater than 1. So we have proven that given that x is less than y, then y over x is greater than 1. Okay, so the second half of the proof of this lemma that I want to use is prove that given y over x is greater than 1 and that they're both positive, prove that that implies that y is greater than x. And so that's what we're given right here. So if y over x is greater than 1, then we may suppose that there exists some k which is greater than 0, such that y over x is equal to 1 plus some k over x for k is greater than 0. Okay? And if this is so, if y over x is equal to 1 plus k over x for k is greater than 0, then we can rewrite 1 plus k over x as x over x, which is equal to 1 plus k over x. And we can combine this fraction to say that y over x is equal to x plus k over x. And if k is greater than 0, and if y is equal to x plus some positive value k, then this means that y must be greater than x, which is what we were trying to prove this time. So we've shown that if y over x is greater than 1, then y is greater than x. Now that we've proven both implications, we can now say that for x and y both greater than 0, x is less than y if and only if y over x is greater than 1. So that's a lemma that we will use in the proof to follow. So now to prove the original theorem, given that 0 is less than a, which is less than b, prove that 1 over a is greater than 1 over b. Starting out with step 1, we'll say that 0 is less than A, which is less than B, and the justification is that's what we're given. And the next thing we'll introduce is that 1 over A times A equals 1, and the justification is that's the definition of the reciprocal. And similarly, we can assert that 1 over B times B equals 1 because of the definition of the reciprocal of B. And the next thing we can say is that 1 over A times A is equal to 1 over B times B because 1 over A times A is equal to 1 and 1 over B times B is equal to 1. So they're both sides are equal to 1. The next thing we can do is take 4 and divide both sides by A. So this A gets over to here on the denominator. And if we divide all of this by A, then this A and this A cancel out. So all we're left with here is this 1 over A is equal to this side divided by A. So 1 over B times B over A. And if we take line 5, we divide both sides by 1 over B. We put 1 over B in the denominator here, they cancel out. So all we have is B over A. And if we divide 1 over A by 1 over B, we get 1 over A over 1 over B is equal to B over A. And on line 7, I have concluded that B over A is greater than 1, and this is justified because on line 1 we said that B and A are both positive, and B is greater than A right here. And look at lemma 1, we said if they're both positive, and if applying it to these, we can say if B is greater than A, then B over A is greater than 1. And on line 8, I'm stating that 1 over A is greater than 0 and 1 over B is greater than 0 because right here we said that A and B are both greater than 0. And as you can see, that kind of goes with the definition of the reciprocal. If x is greater than 0, then 1 over x must be greater than 0 because a positive times a negative number cannot equal 1. So we might okay. On line 9 here, I have concluded that 1 over A over 1 over B is greater than 1, justified by lines 6 and 7, because on line 6, I'm saying that 1 over A over 1 over B is equal to B over A, and on line 7, B over A is greater than 1. So that means that 1 over A over 1 over B has to be greater than 1. And finally, because of line 9 and because of this lemma, we can say that 1 over A is greater than 1 over B, which is what we set out to prove. Lastly, the problem said, why is the restriction that A is greater than 0 necessary? Well, I rephrased it. I said, what if the 0 is less than A constraint is not included? Now, with a proof, a mathematical proof of something that has to do with numbers, if you want to prove that something is true, you need to prove that it's true in some way other than by cases, individual cases, unless you happen to be working on a discrete problem. But given that A could be any of an infinite number of values and B could be an infinite number of values, you can't practically prove a problem by cases when there's an infinite number of possible values. But disproving something just takes one example where it doesn't hold up, as we'll see in a second. So here we are, we said let A equal -6 and B equals 2. We still have A less than B, but we've done away with the constraint that A must be greater than 0. We're saying let A be a negative value, but we still have A less than B. So does this theorem still work without this part? A is less than B. Is 1 over A greater than 1 over B? Let's see. A is -6, so 1 over A is -1/6. B is 2, so B is 1/2. This is 1 over A. This is 1 over B. The theorem says that 1 over A is supposed to be greater than 1 over B when B is greater than A, but no. 1/2 is greater than -1/6. So this theorem breaks when we don't have the constraint that A is greater than 0 and less than B. We showed that just by one example. There's actually an infinite number of examples where this theorem doesn't hold up when we don't have the constraint that A is greater than 0. This question says, if A is less than B and C is less than D, is A times C is less than B times D always true? Think about this. Why don't you draw a number line? You could, and try different combinations. What properties of multiplication and numbers could you use to come up with a situation where this isn't true? Remember, to disprove something, all you need is a single example. Here's one counterexample. You can come up with an infinite number of them. Look at this. If we said A is -3, B is -2, and look, A is less than B because on the number line, A is to the left of B. C is 1, D is 2. Now C is less than D because C is to the left of 2 on the number line. So we have A is less than B and C is less than D. But AC is -3 times 1, which is -3. Okay, so AC is -3. B is -2. D is 2. -2 times 2 is -4. So BD is -4. So look, AC is not less than BD. BD is less than AC. So here's an example where A is less than B and C is less than D, but AC is not less than BD. So that's just one example. So this is false. If A is less than B and C is less than D, AC is not always less than BD. This problem says, find the interval of solutions for the inequality 3x plus 2 over 2x minus 7 is less than 0. So how would you go about solving this problem? Think what you know about fractions. If the numerator and denominator are both positive, then what's the sign of the fraction? Positive divided by positive is positive, right? Now, what if the numerator and denominator are both negative? Then the fraction will be positive. If the numerator is 0 and the denominator is non-zero, because the denominator cannot be 0, then it will be equal to 0. So what situation do you need to find for the denominator and the numerator for the fraction to be negative? You need one of them to be positive and the other to be negative. So that's what we'll look for. So case 1, we'll try to see if there's any value of x for which 3x plus 2 can be negative and 2x minus 7 can be positive. So I set these two inequalities up right here. So for this one, 3x plus 2 less than 0. I want to get it just for x. So I can subtract 2 from both sides. Then I've got 3x is less than negative 2. Now, to get to x, we can divide both sides by 3. 3 over 3 just leaves 3x over 3 just leaves the x. It is less than negative 2 divided by 3, negative 2/3. So for this one, we've got x less than negative 2/3. Now we'll see if we can find an interval for which 2x minus 7 is greater than 0. I want to get this negative 7 over here, so I'll add 7 to both sides. That leaves 2x greater than 0 plus 7 is 7. To get this x by itself, I'll divide both sides by 2. 2x over 2 is just x, is greater than 7/2. Now we have to compare these two results to see if they are compatible. Can x be less than negative 2/3 and at the same time greater than 7/2? It's impossible. So this is impossible. You cannot have the denominator negative and the numerator positive. That won't work. So we have to try the other possibility. We'll try to show what values of x make it so that 3x plus 2 is greater than 0 and 2x minus 7 is less than 0. Once again, we can subtract 2 from both sides. We got 3x is greater than negative 2. Divide both sides by 3. X is greater than negative 2/3. Okay. Now over on this one, we can add 7 to both sides. And 2x is less than 7. Divide both sides by 2. And x is less than 7/2. And this is possible. There is an interval between negative 2/3 and 7/2. During this interval, this expression is negative. So the interval of solutions, not including the boundaries, is from negative 2/3 to 7/2, not including negative 2/3 and 7/2. It's actually undefined at 7/2 because the denominator cannot be 0. And at negative 2/3, it is equal to 0. So in this open interval, this quotient is negative.